All right, let's jump right into this explainer. Today we're tackling something that, let's be honest, drives a lot of Cambridge, AS, and A-level physics students absolutely crazy. We are talking about mastering errors, uncertainties, and precision for syllabus 9702. Most students lose incredibly easy marks on this topic, and it's not because they aren't smart. It's because they rely on superficial memorization rather than actual, deep analytical thinking. But by the end of our time together today, you definitely won't be one of them. We're going to decode exactly what the examiners are desperately looking for, and we'll focus heavily on the benchmarks that separate a pretty good physics student from a truly outstanding one. Every single mark counts, so let's get into it.
Here's our roadmap for today. We'll start off with the core physics foundations, move right into the procedural framework, highlight some top examiner warnings, and then wrap the whole thing up with evaluation and critical analysis.
Okay, Section 1, the core physics foundations. Let's lay down the groundwork.
So, right out of the gate, we really have to ask ourselves a crucial question. Why is it that so many smart students find the distinction between these basic terminologies so incredibly hard? I mean, the fundamental principles of this topic demand way more than just a passing familiarity. Yet paper after paper, year after year, students stumble over the exact same hurdles. They mix up concepts, they use totally wrong terminology, and they just fail to demonstrate the systematic analysis that the Cambridge Assessment Framework absolutely prioritizes.
And honestly, this quote brilliantly illustrates the core issue. This is straight from the principal examiner reports, guys. They explicitly say that the classic mistake is providing generic answers that are not specific to the question context. Top-performing Cambridge students, they don't do that. They exhibit connected, conceptual understanding. They don't just regurgitate a textbook definition they memorized the night before, they apply evidence-based reasoning to unfamiliar, highly specific contexts. If you take away literally only one thing from this entire explainer, please let it be this. Always link every single point you make back to the specific scenario in front of you.
So to do that, a crucial starting point is actively contrasting paired concepts. Look at the comparison here on screen. First up, we've got systematic errors. Think of these as consistent, predictable deviations. They skew your data in one specific direction every single time. It's like, imagine using a poorly calibrated digital scale that always reads 2 grams too heavy. It's systematically wrong. Then, on the flip side, we have random errors. These are unpredictable statistical fluctuations that scatter your data both above and below the true value, like a sudden gust of wind hitting your experiment. Grasping this difference conceptually, and not just broadly, is your absolute first academic benchmark.
Next up, and this is a big one, you must rigorously separate precision from accuracy. Mixing these two up is a surefire way to bleed marks when evaluating your evidence quality. Precision is all about the consistency and exactness of your repeated measurements. Think of it like throwing darts. If you throw 5 darts and they all hit the exact same spot in the bottom corner of the board, you are highly precise. Even though you miss the bullseye entirely, your precision is great. Accuracy, on the other hand, is the closeness of your measurement to the actual true value, hitting that bullseye. Top-performing students can look at an experiment and clearly articulate whether it suffers from an accuracy problem, a precision problem, or maybe even both, and they use the correct terminology every single time.
All right, now that those core definitions are locked in, let's move on to Section 2, the procedural framework.
Now, what's really fascinating here is what we call the method mark strategy. Look, examiners prioritize your analytical depth and your process way over just a superficial final numerical answer. If you're calculating the final uncertainty of a really complex system, the examiner wants to see the architecture of your thought process. It's like a giant puzzle for them to grade. They want to see clear notation, correct headings, and logical steps. The final number, that's really just the tip of the iceberg. The method itself is where the bulk of your marks are actually hiding.
So how do we actually capture those method marks? Well, your problem solving must follow this precise 3-step procedural framework. First, you deconstruct the given information. You extract the relevant data from the texts and tables they give you. Second, you solve systematically, in logical steps. You've got to break down complex uncertainty additions into manageable bite-sized chunks. And third, you evaluate and check for reasonableness. Take a step back and ask yourself, wait, does my final uncertainty actually make sense given the physical constraints of this experiment?
And when you're in the weeds executing your analysis, especially for something technically demanding like uncertainty addition, you really need to systematically process your data through these 5 strict conventions. It ensures your notation is crystal clear. 1. Identify the key elements of the formula. 2. Apply the relevant principles of uncertainty physics. 3. Execute your analysis with super clear working. 4. Verify your results. And finally, 5. Present the information following strict conventions.
Use proper headings, correct terminology, the appropriate formats, and clear annotation. Following this sequence literally transforms a messy, panicked calculation into a professional, undeniable answer that examiners love to see.
But hey, even with a perfect framework, you can easily fall into common traps. That brings us to Section 3, Top Examiner Warnings.
These right here are the literal red flags, straight from the principal examiner reports. First, answers are often far too vague. When an examiner asks for the source of an error, they want specific, concrete details, not just some generalized guess. Second, students are constantly forgetting format and presentation conventions. If you don't use the correct format or clear annotation, you are literally throwing marks away. And third, echoing our point from earlier, answers are not specific to the given context. Your answer absolutely must live and breathe within the world of the specific experiment printed on your exam paper.
To prevent those vague answers, I highly recommend creating a memory hack. Something like a custom acronym so you can systematically list out every single factor affecting precision and accuracy. Because let's face it, when the clock is ticking down in the exam room and the pressure is on, having a quick mental checklist ensures you systematically process the problem. You can quickly evaluate instrument calibration, environmental factors, observer techniques, and equipment limitations without missing a single beat. It's a real lifesaver.
Finally, let's step into Section 4, the valuation and critical analysis. This is the stuff that pushes a good grade into an outstanding grade. Evaluating the quality of evidence isn't just about making a wild guess. You must systematically document it. This matrix here, this is top-tier analysis. It requires you to clearly identify the limitations of the experimental setup. You must state the assumptions you made during your data collection. You need to be completely open to alternative interpretations of the data. And most importantly, you must explicitly show the effect of these factors on your final conclusions. For example, if your systematic error is high, how exactly does that alter your final recommended value? You have to spell it out.
Mastering this kind of data interpretation requires you to execute all of these critical skills seamlessly. You have to extract the right data from texts and tables. You must interpret the relationships within that data, like figuring out how the uncertainty scales as the measured value increases. From there, you draw solid evidence-based conclusions. And finally, you make justified recommendations. Doing the whole shebang is exactly how you demonstrate that connected conceptual understanding the syllabus emphasizes so heavily.
So, I want to leave you with this provocative question to really challenge how you approach your very next Cambridge 9702 pass paper. When you sit down to practice, is your answer going to be just another generic textbook guess? Or are you going to use this procedural framework to deliver a specific, context-driven evaluation of the evidence? By shifting your focus from just getting that final number to truly mastering the method, applying precise terminology, and strictly following the context of the question, you are perfectly positioning yourself for maximum marks. Keep practicing these structures, and I promise you the results will absolutely speak for themselves.